So welcome back. Let's talk about what we'd like to accomplish tonight. So I'm going to talk about the exam briefly, and then I'm happy to have long conversations with the individuals. Then I want to talk about a class exercise which will turn into a homework, about fitting a model to seasonal data. And then we're going to get on to exponential smoothing, which is used a lot in business. And we'll see that that's a very special form of an ARIMA model. And I'll try and control myself because I usually rant at this. And then we'll start something which will go a couple of weeks. What about if you want to put predictors in? Right? What if you know the number of restaurants in Chipotle? The more restaurants, the more sales, presumably. So we will do that. But first, let's talk about the exam. I was very pleased with the overall performance. The median score was 45 out of 50 at A. So essentially half the class got an A. That's great. A few people will be a little bit disappointed with what they get, but you can always make things up on the final and the project and the homeworks. Well, the other thing I want to talk about tonight is I put up a document which gives you guidance about what I'm looking for in the project proposal. We'll talk about that. So, I just want to go through a few highlights of the test. There were what I call sleeper questions, which I had no clue would be, that they would be. So let me explain. Question 1, is this series stationary, log sales? No, it has increasing mean. Is this the first differences stationary? No, there's very strong seasonality. A small number of folks said the mean and variance was the same and ignored the seasonality part. Yeah, they were winding me up. I was talking to myself. And then situation 1, situation 2, and situation 3, they were pretty interesting, weren't they? What does the first one look like? It looks like AR2, doesn't it? The PACF cuts off. What does the second one look like? It looks like MA2 because the ACF cuts off. What does situation 3 look like? It's hard to tell, right? Order regressive moving average, but we don't know the order because the ACF and the PACF provides no information, right? Good. So we've learned a lot this semester. That's great. People did very well with that. They did very well with SCAN and ESACF. So I have a new magic recipe for producing data where these things are more clear. So we don't have arguments about where to draw the lines. Good? Yes, good. So that one went well. And then I put in an MA2. I was thinking about doing ARMA because I'd done AR and MA, but I thought, I haven't done MA2, let's do MA2. Most people got it, but there were a few that got themselves a bit confused. Right, a bit confused. But overall, that was pretty good. And then these miles travelled. Whether the statements are true or false. So, if you look at the series, what do you see about the miles travelled? The miles travelled is not a stationary series, right?
Yep.
Right? The mean is changing over time. The ACF takes a long time to die out. So, stop, do not pass go, difference the data, right? You can't say anything until you difference the data, right? We can't even begin to think about what order it should be until we have a stationary time series. And that's what I call a memorial question, because there was a student a few years ago who drove me crazy for the whole semester about this issue. So I had to have a memorial question. Are we good? It makes me smile.
Did everybody get it right?
No.
Question.
Yes, question.
Yeah, this is Alejandro. So the question says, into the ARIMA model. So in the ARIMA, I can do the difference already. So I wonder if this is subject to interpretation.
No, well again, Alejandro, what are you going to put for P and what are you going to put for Q? You can put D equals 1, yeah, I give you that. But what are you going to put for P and what are you going to put for Q? Those plots give you no information for that. Okay?
But you say ARIMA group model, so I'm just gonna put like a a range.
Yeah, so tell me what the biggest value you can put. It doesn't give you any information. Right?
Okay, thank you.
So again, I wasn't trying to be smart. This is a very important fact. We only model stationary time series, right? Yes? Again, I'm being tortured. I've got one breath left, and I'm going to say that again. Yes? Valid models is very important in my statistical religion. Yes? The differences appear to be stationary. I think that's reasonable. The ACF and the PACF of the different series looks like MA1. That seems reasonable, doesn't it?
Yep.
Because the ACF cuts off that lag line. Okay. So, finding series, right? I cycle through about 20 to find a few to put on the test. Yes? Anyway. Gross domestic income in billions. The question's about valid parsimonious models, right? We have two valid models because they pass the Box-Lyon, right? Box-Lyon white noise test. We don't have parsimony in the model in the left-hand column because there are two of the coefficients, the MA2, the MA3, and one of the AI coefficients that's not significant. That was relatively straightforward and people did well. Then we get to question 7. My mother had 4 sons in 4.5 years, and she said to me that after each one, she said she'd never have another child again, and she had cesarean sections for each one. So this is what I'm like with question 7. This took me the whole of Saturday to grade this. Because you can ignore my directions and come up with better models, that's fine. But what I have to do is actually fit everybody's other model. So where are the answers? Let's look at the last question. So, the data is non-stationary, so you difference the data, right? You difference the data. When you difference the data, what is a possibility? Some people said a REMA, but the trouble with the REMA is we don't know P and we don't know Q, right? And if you're stuck, you say, okay, the PACF cuts off after lag 3, yes? So you say AR3, but the 2 term is not really significant. You can try AR1. If you try AR1, it's not valid, so you should. If it was me, I wouldn't be able to control myself. I want to go back and put in the 2nd and the 3rd order terms to make it valid, yes? Then when you do the model group, you find it's a REMA 111. Now some people did double differences and you can get a simpler model, which will actually have a lower SPC. I had no problem with that. Right? Anything's possible. The most important thing is to put clear explanations, right? So they've had many of these time series competitions around the world. 2 faculty members at A&M won a worldwide conference once. And you can have 2 models that are quite different give similarly good predictions. It's all about logical thinking. Anyway, as I say, I was very pleased with the test. It demonstrates we've learned quite a lot and the basics are well known, well understood. It's just when we get to putting this with some of the series, that's when the rubber hits the road. Okay. Any questions? I think we're good, right? All right. So let's talk about what we're going to start as a class exercise in your groups, and I'll walk around what I want us to do is to look at operating revenues for Southwest Airlines. Interesting, isn't it? If you look, I think there's increasing variance. There's increasing variance in the top plot. That goes away and you take the log. Notice there's a big jump up here. Does anybody know what happened in 2011 quarter 2? It's a level shift. Suds.
Did they buy AirTran?
Yeah, they bought AirTrans. Okay? So, here's the deal, guys, and it's very informative, this thing. So what you're going to do is you're going to look at the ACF and the PACF of the suitably difference data. We're going to do first differences. We're going to see if the seasonality is still strong. If the seasonality is still strong, we're going to do seasonal differences. Then we're going to look at the ACF and the PACF and choose a series. Are we good? Then we're going to do a ARIMA model group, and we're going to see if you get the same as the ARIMA model group. Scouts on it, I did. Are we good? And then we put this in SAS and look for outliers and level shifts. Then you put those in and run, and then I got estimates may have not converged.
Say that a lot.
Yeah. Yeah. Well, I wouldn't say a lot, but it happens. Don't want to get sued. SAS is a great product. I'm the SAS Distinguished Professor this year. Great product. Here, listen, here we go. So, maximum likelihood can sometimes get trapped in a local minimum. Right? And so it's a bit like if you've ever been to Machu Picchu and looked over the edge. Imagine if you were wandering through that bush, right? You could get stuck somewhere and go, I have no idea where I should go. That's what happens to the algorithms. So something that works better in those circumstances is called CLS, conditional least squares. So if you get something that doesn't converge, what typically happens is it wants to fit an MA parameter and it gets something, a theta close to 1, right in that invertibility edge, and it gets stuck there. So we're going to use conditional least squares. Are we good? So MA works on the original data. When you put the outliers and the level shifts in the model that I chose, it said with maximum likelihood this may not have converged. So then I just reran and removed method equals ML and replaced that by method equals CLS. Are we good?
I'll be my hurricane data.
Good.
Now, Sridhar,
Yes.
if I step back,
Yeah.
the log series, that's not stationary, so you didn't have to.
I'm going to have to first difference that and
So that's what
seasonally
you
difference.
know,
Right? This one. I'm going to use this one.
Yeah. So but it's not a stationary series, right?
Not yet. So I'm going to have to do some differencing.
Right. So you're developing the model using the difference.
Using the difference.
Okay.
Right? I'm going to use first differencing and I'm going to use seasonal differencing. Give up my secret sauce. Okay? All I did was transform to make the variance constant. Are we okay? Now we haven't had much practice with fitting seasonal ARIMA models yet, have we? So here we go. Here we go, here we go, here we go. And then you have to come up with, you get predictions for log operating revenues, and then you reverse the log by exponentiating and see how close you get. And you write it up and hand it in as a homework. Are we good?
So,
Yes, and to be fair, I've done this in the past, and I didn't tell them about this step, which was a bit harsh, really, wasn't it? It was a bit harsh, and then I got lots of questions, and what happened here, what did we do wrong, so I'm telling you up front. But who knows, this is your group. You may come up with a whole different family of models where this doesn't happen. Any questions about how this works? Yeah.
So the CLS, if it does converge, what is the difference to use versus maximum likelihood?
So if you, in 99% of cases, maximum likelihood and conditional least squares give very similar estimates. Right? Conditional least squares is like the all-terrain vehicle. So when you use this SAS, Artificial Intelligence, SAS Forecast Studio, it doesn't do maximum likelihood, it does conditional least squares.
So what is the advantage of maximum likelihood?
Well, what's the advantage of maximum likelihood? I mean, the old school people would say it's more of the purest thing. You actually have a model where you've got this underlying model with, so it's really, what's the advantage? There isn't one, it's historical.
Okay.
Okay? People started with maximum likelihood in the 1980s when they coded this stuff. And if you think about a Bayesian equivalent, what you're going to do is start with a likelihood and put a prior on it. So it's easier to compare maximum likelihood estimates with Bayesian estimates. But I'm not fast. I'm not fast. Again, I see my job is to show you when things work and to show you when things don't work so you know what to do when you fall down a rabbit hole. Yes? So this things not converging happens a bunch. Right? Happens a bunch. When you get the theta close to them. So, any questions? Are we good? We have a good plan? So I want you to go away for 35 minutes and get started. Would be good if you got down to through step 5. It's not, it shouldn't take long. That is, you've looked at the difference, the data, looked at the ACF and the PACF, right? You put it into SAS. I provide both the SAS version of the data and the jump version of the data. Okay? And I want you to do this in your groups, and I'll wander around and help.
Let's get it.
Okay?
14 and 8, right?
Yeah. 35 minutes, right? Is that what I said?
It said 34, but we'll take 35.
Data set is not original batch.
So, 7:40. I'll be back 7:40 Central Time.
Here's a folder.
Okay, so welcome back. I got around to most of the groups, I think. It was pretty interesting, the seasonal part, wasn't it? So we're using the same logic that we did in the non-seasonal part to look at lags 4, 8, 12, 16. If it's monthly data, we look lags 12, 24, 36. Are we good? We'll get a lot of practice as time goes forward with that. So let's talk about the term project. That's the final thing that I need you to do. Here's what I need for 6 p.m. next Thursday. Alright, so the first thing is, why are we interested in this? So what's the setting? What questions are you trying to answer? So, you can go to the Census Bureau and find data on essentially anything, and I'm going to ask myself, why are you interested in that? So motivate the problem. Is that a reasonable request?
Reasonable.
Reasonable. Good. Describe all the variables included in the data. Later on, I'm going to ask you to attach the data because I want to fit some models to make sure you're not going down the wrong blind alley. Does that seem reasonable? Mm-hmm. And in order for me to do that, I need to know what's in every column. Yes? So if you send me a spreadsheet with 99 columns, I want to know what's in all 99 columns. If you don't need the 99 columns, please don't send me the 99 columns. Is that good? Mm-hmm. So why is it of interest to model the outcome curve? Again, I seem to be labouring this point. But we're not here to do a science project to come up with a beautiful model for something that's irrelevant, right? Describe the time frame, start date, end date, and how far ahead in time do you want the model to predict? So imagine you find it's MA1 or AR1 and you want to predict 24 periods in advance. Got a problem, Houston, haven't we? Yes? Provide the entire data set or a complete subset. And then what sort of time series models do you expect to fit? So I had a group a few years ago, the first year I taught this, I wasn't so rigid about this. We wanted to try and predict things to do with oil price. And they did about 10 times the work of any other group, and they found nothing. Right? They really found nothing. Because it's hard to predict oil prices. It's hard to predict oil prices' effects on things in the US. In my experience, the United States of America, with all due respect, because I'm foreign, is one of the greatest misnomers. Because it's not united. Things are different in different regions. So if you want to look at effects on building starts, building completions, you need to do that on a regional basis. Even sales. So there are a few rules that I've gotten over the years, so I'm going to try and help people so we don't waste time. Does that sound like a good plan? Yes? And we know enough now to be a little bit dangerous, don't we? We know about seasonality. We know about that we can use a time series to predict another time series. We'll learn how to do that. Are we good? And I don't need pages and pages. Brief is good. You know what I like. They you know how to wind me up, mate, don't you?
I know how to wind you
You
up.
don't want to do that, do you?
No,
Yeah, let's not do that.
no. R
So,
squared
one
doesn't mind.
question here.
Yes?
So, for example, I noticed in class, let's say that we were trying to
Here's
predict
the
net
one.
sales of Amazon.
Yep, Amazon, yep. We did that in class, yep.
Yeah. So I just put it out as an example, right?
Yep.
So for that data in particular, we have just time and Amazon sales.
Yep.
So if we have a data set that is similar to that format, I mean, just time times error, time times something else, is that good enough, or you want something more in the?
Well, imagine if you sent me Amazon sales and I come back with a model that says it's 011011. That's a bit too trivial, isn't it?
Correct.
Okay, so I don't want something that's like a homework in week 3, and I don't want something where you're going to spend 100 hours and find nothing. I want something in between. But let's think about Amazon sales. Could there be a forward predictor of Amazon sales?
Sorry, I didn't catch the last part you said.
So Amazon sales. So who are their biggest competitors?
Walmart.
Walmart. So imagine you were going to do a multivariate model of Amazon and Walmart and see how they move together. That would be a brilliant project. Okay? So if you want to do competitors, then that's a good project.
But is that one like the example we did with Lowe's and Home Depot?
Yes, the Lowe's and Home Depot one. We would fit separate models to Lowe's and Home Depot, and we'll learn towards the end how to
Transfer.
model them together. So you're going to be thrill seekers right at the end to do that. So does that answer your question, Alejandro?
Yes, it does, thanks.
I would find something a little bit more challenging than that, something where you think you have some predictors, or something that's a little bit unique. Yes?
Okay,
Okay?
so are you suggesting like having 2 variables instead of 1 or things like that, like we saw in the project?
And no, you don't have to have 2 variables in a one. No. So one group did, last year, one of the most challenging ones was applications for Social Security. And they fit a different model to different regions. Another one was turkey sales, because somebody worked for Butterball Turkey. And they had different models for different regions. And man, were they different. Another group had cheese sales. You know, what cheeses me off in Texas is people aren't sophisticated about cheese. If you went to a dinner party in Sydney or Melbourne, the cheese course with the wine would be spectacular. And now here they just think you're weird. Foreign dudes eating cheese. So the guy who worked for a food company, he was in charge of cheese. So he did cheese models around the country. It was really fascinating. So Alejandro, you can do one outcome variable, especially if you have to have a different model for different reasons. Isn't that interesting, right? Yes.
Perfect, got it.
Good. You actually enjoy this part of my job. These weird things. any questions? No, we're good.
Dr. Sridhar, in the same slide deck, I see there's a, what is that?
That's the actual final thing. That's what you've got to do at the end.
Okay.
So I said, what I've done, based on past feedback, is don't just tell me what we need to do at the start, tell me what the end product needs to look like.
Okay.
Is that good? Yeah?
So that example, Dr. Shearer, that you mentioned about the regions,
Yeah.
we can go down the rabbit hole and this thing can grow. What do you expect? Only one data set, like one region? Or?
No, again, if you've just got something where it's sales, right, of one company's sales, and you had, so what happened with each of those was it was difficult to get a model.
Yep.
To fit the whole country. So the natural thing is to say break it up in regions. Red light camera tickets in Chicago, MS statistics students had trouble getting a model to fit the whole city because the neighborhoods are different. So you sort of force yourself that way.
Okay.
But again, think about it. Neighborhoods. The ones during the week where there's a lot of traffic, there's a lot of red light camera tickets, yes? And in the residential neighborhoods, there's more traffic on the weekends. You're going to be inherently different, yes? Yeah.
Is there a way to cluster it or structure it? I think you mentioned last time something about similarity features. What would those be? Or
It's usually a subject matter expert. So the Turkey guy was great.
Yeah.
Because he'd say, if you're from this part of the country, you're interested in such and such. So a subject matter expert. Right. All right, so let's look at exponential smoothing. You go to people in companies that do time series, and they think of exponential smoothing often. So if you go, so there was a snack food manufacturer, can't tell you anything, they had weekly sales of the snack food in every supermarket in Texas and Florida. And Mike Speed and I said we could get a better model than their exponential smoothing. And then it turned out to be hard. But we did. We did. But we need to understand what exponential smoothing is.
Bless you.
So we consider time series models called exponential smoothing models, and the current value of y is modeled as a weighted average of earlier values, where the weights decrease as y is more distant in time. So we're going to model today as a weighted average of yesterday, the day before, right, where the weights decrease the further you go back. Makes sense, doesn't it?
Yep.
So let's look at the definition of exponential smoothing in its simplest setting. We're not going to assume seasonality. We're not going to assume trend. We can put all that fancy schmancy stuff on later. So this says the prediction at time t is alpha, a number between 0 and 1, of yt minus 1, what happened yesterday. We're going to predict today as a function of yesterday, a fraction of yesterday, and 1 minus our prediction of yesterday. So y hat 2 is alpha y 1 plus 1 minus alpha y hat 1. So what we're going to do here is we're going to do some math, just some algebra, substituting in equations.
Dr. Shi,
Yes,
could you repeat what you said about Formula 1?
Formula 1. Y hat t is alpha times yt minus 1 plus 1 minus alpha times y hat t minus 1.
No, but the way you explained it.
So what y hat t is the prediction of today. We get up this morning, we have a prediction of what the value is going to be today. Okay? Yes. And we have what the value was yesterday. Yes. plus what our prediction of yesterday was. Y hat t minus 1. So y hat Tuesday is alpha y of Monday plus 1 minus alpha y hat of Monday. And you look at that and go, oh, that's puzzling, isn't it?
Mhm.
It's like, what crazy person dreamed that up? It's the way I would think. So then I think, okay, let's unravel this so we can get a straightforward formula about what this is actually doing. That seem reasonable? So then I write out the first few terms, y hat 2, y hat 3, y hat 4, are we good? Then I'm going to write y hat 3 in terms of y1. So y hat 3 is alpha y2 plus 1 minus alpha y2 hat. So I'm going to take the y2 hat from up here, yes, and I'm going to plug it in. Are we good? And then I'm going to simplify. So this is saying y hat 3 is alpha y2 plus 1 minus alpha times alpha y1 plus 1 minus alpha squared y1 hat. Right? Now, y4 hat is, by definition, alpha y3 plus 1 minus alpha y3 hat. Now we know what y3 hat is. Y3 hat is this mess. We good? Now look at the pattern. Y hat 4 is equal to alpha y3 plus 1 minus alpha times alpha y2 plus 1 minus alpha squared times alpha y1 plus 1 minus alpha cubed y1 hat. So we can keep doing this until the cows come home, as my dear old mother would say. Are we good?
Yep.
And then we're going to get a formula that says y hat t is alpha yt minus 1, 1 minus alpha times alpha yt minus 2, 1 minus alpha squared alpha yt minus 3, etc., right? And that's what the words were that says these factors get lower and lower, smaller and smaller as you get further back in time, and then there's this weirdo jobby at the end. The first point, right? It just stays there. Let's ignore that for a moment. But do we understand where I got these weights on yt minus 1, yt minus 2, etc.? We good?
Is this sometimes called exponential moving average?
Yes. If you're going to be loosey-goosey.
Sure.
Okay? Yes.
Very nice.
I need your help, Sarah, or I'm stuck. I'll go forward to you.
No, listen, that's why I'm okay with that. Because why
Yeah,
was
what did you do?
interfered with, yeah. And there was time, you and Law had the same one, I'd be moving it, and someone else is confused. Yeah.
Yeah, so for some reason,
Okay, so just I have to use these arrows. Okay, thank you. That's good. So, let's look at what happens using this formula. So, formula 1 we've shown gets us to formula 2, right? Now, if alpha is 0.2, then you get 0.2 times 0.8, which is 0.16. Right? See how that works? So what I've done is done a bunch of examples. What happens with the weights if you take alpha 0.2, alpha 0.4, alpha 0.6, alpha 0.8? Are we good with that? Let's do yt minus 2. Yt minus 2 is 1 minus alpha. So that's in the first case 0.8 times 0.2, which gives you 0.16. See that? And then for the next one, we're going to square the 0.8 and multiply by 0.2 and we get 0.120. So you see it goes down, and the higher the alpha, the slower it goes down. Then you have to ask yourself, what do we do for y hat 1? This very first one. So it's common for folks to use y hat 1 as the actual value of y hat 1. Especially when t is large. Because if you do 1 minus alpha to the t minus 1 when t is 100, the multiplier is 0.0004 zeros and a 3. So most people will say this term here is like the Shakespearean play, much ado about nothing. You're only going to mess with decimal places that are so far off that you're not interested. But it is a potential problem. It's a loosey-goosey part of the algorithm, isn't it? But the point here is, what we're doing is using weights which quickly decay. Right? They quickly decay, don't they? And they're a bit arbitrary. How did they dream up this formula? Right? How did they dream up this formula? Now, how do we choose alpha? Well, the one way to do it, and the way that Jump does it, is let's choose alpha to minimise the mean squared error. The sum of the squared differences between the actual value of y and the predicted value of y squared. Alright? And there's n minus 1. Seems reasonable. We're going to minimise the average squared error. Okay. Forward. Let's do this for the Berkshire Hathaway quarterly revenue data. Okay? This is the same data as we've seen before. And you get your time series plot. Now, please don't do this. You'll see we're doing sort of a little bit of a bad thing, but we're just doing it for illustration. Alright? So, you go down and you say you want a smoothing model. And the smoothing model is called simple exponential smoothing. You can do double, you can do linear, you can do seasonal, you can do winter method. So there are a whole series of people that whatever ARIMA model that we would want to fit, they're going to fit some exponential smoothing. Now, we're going to constrain alpha to be between 0 and 1. Right? That means we ensure the weights get smaller as we go further back in time. Seems reasonable?
So why would it be any different? Because that's your starting assumption.
Well, again, it's like MA. If it's not invertible, it's possible to get solutions sometimes where this is a crazy model where the best solution is alpha is not between 0 and 1. Yeah? So, we do that, our estimate of alpha is 0.72477. Here's our model fit. Yes, we even get standard errors and t ratios. We get r squared. Yes?
Are you actually predicting anything at this point?
Yeah, we're going to predict the next point. So remember we did this as a homework. We did up to 2017 quarter 1 and predict 2017 quarter number 2. I'm going to show you the whole 9 yards and come up with a beautiful prediction. Okay? So, the predictions are a straight line. Why is that? It says, once I predict the next value, that every prediction after that is the same value.
Because you're not predicting anything, so all the values after...
Yeah, let's look at what it does from an equation, right? Y hat t is alpha yt minus 1 plus 1 minus alpha yt minus 1.
And that's 0, so everything becomes closer to yt minus 1.
Well, the thing is that you don't know what yn plus 1 is because you've only got up to yn, so we're going to predict it by yn plus 1 hat. We get alpha plus 1 minus alpha, that cancels out. So yn plus 2 hat is equal to yn plus 1 hat. Right? So, are we good? It's just a simple mathematical consequence. This works great for the next observation, but after that you're in more trouble than the early settlers of Australia. Yes?
Looks like a scam.
Looks like a scam. Well, look, go and talk to people who do time series. They'd be jumping off the seats now, beat me with a stick. And I'm trying to be fair. Okay? Have a look at the residuals. They're a thing of beauty.
About the week.
I'm weeping, JT, with you, mate. Got the tissues. So we have a valid model, don't we? We have a valid model. Now, what is our training in? Our training is in ARIMA models, because we understand ARIMA models, we know what it's doing. This is a bit loosey-goosey, isn't it? Yes? So, what I'm going to show you here, and I'm going to let you do the math in your own time, that exponential smoothing is equivalent to fitting ARIMA 011. Model with mean 0. That's very important. That when you do exponential smoothing, you are saying the correct model for that data is ARIMA 011 with 0 mean. Now, we can look at the math. That hasn't been gone that well tonight. So let's actually do side-by-side comparisons of 011 with 0 mean. Get it? You know how to do that? We love this, right? What happens? There they are, side by side. What do you see? Everything is exactly the same. Yes? Sum of squared errors, the variance estimate, the standard deviation, AIC, SBC, R squared adjusted, MAPE, MAE, minus twice the log likelihood. The only difference is in the IMA, in the MA, theta is 1 minus alpha. So, if you talk to the people at work who love exponential smoothing, what they're doing is fitting a subset of ARIMA models. And each jiggery-pokery thing is a different ARIMA model, right?
P-values are different, why is that?
Yeah, well, the p-values are a little bit different because this is 1 minus alpha, and this is alpha. Yeah? But it's still estimating the same thing, right? So,
Why is it so popular?
I'm not a psychologist. Well, let's think about it. If you look historically, before there was fancy ARIMA modeling with maximum likelihood, you could do this with Excel, right?
But is it popular though? Is that true?
It is. So again, if you take people who work in retail, sales, they go back to the company after this lecture and there's a lot of back and forth. So I don't want to go on the recording and mention the companies by name. But again, snack food manufacturer. You love their snack foods. I've seen you eat some of them. Lots of them here. Can't tell you what not because I'll give it away. They had their exponential smoothing model and Mike Speed, who's a genius, and I said, oh, look at that, we'll just beat it. Weekly sales, every supermarket in Texas and Florida. That's not big data, that's giant data. We did. So, to be fair, those guys can do their stuff, but it's kind of homegrown. I would be much better at, you know what I'm like, valid models with reasoning. We look at ACFs and PACFs and pick terms, don't we? We don't do patches. So like you say, why did you have that? Oh, that's the effect due to Thanksgiving. Why did you have this? Well, that's the effect due to this. It's like, dude, there's this old exercise book with 5 guys have written in it over the years they've found things. Well, that's great, but I would much rather do a reasoned, a REMA modelling approach. Sam,
If you go back to the other slide,
what
and
number?
13.
Yeah.
The magnitude of the coefficients are so different because with the exponential smoothing, you're not doing it on the difference, right?
So, the exponential smoothing is on the data, right? It's on the data. But I show you, and you can do this in your own time, that if you go through the math, that a REMA 011 with 0 mean comes down to their equation.
Right, so you're not differencing the smoothing data before.
So, the exponential smoothing guys, they're not doing any differencing.
Yeah, okay.
But when we're looking at what they're doing is an MA model on the differences, making the mean 0. Okay?
But
They won't tell you
my-
that.
It works out the same.
They don't tell you that. So that's why I like this, because it's looking into their work, right? Yes? Understanding what they do. So let's move forward before we get into all of the argument. So, these two things. IMA 1-1 no intercept, simple exponential smoothing. They give you everything exactly the same in model comparison. Same estimates, the same forecasts, the same confidence bands, right? So when I saw this, I couldn't believe it. I thought it was just one of the most brilliant pieces of little math that says, this is what they're doing. For years, people have said, no, you professors, you're just too theoretical. Well, dude, that's what you're doing. Yeah.
Dr. Sridhar, how did you get the model comparison for a simple exponential?
So
It's the
if
same
you
way?
fit any models in JUMP, it puts them in the model comparison. If you choose them by hand. Okay? Now, when we did this, what did we do? With reason argument, we fit an IMA 1-1 and we allowed an intercept. And look at the intercept. It's 808. And if you think about the differences, this is Warren Buffett, the legend man. And this is saying that the quarterly difference in revenue, these other dudes are saying the quarterly difference has a mean of 0? No, 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 no. Mr. Buffett would be very unhappy with that, yes? Yes? And have a look at the difference in the predictions. Look at these things. Look at this versus this. They go up, right? Yes? So this is my first problem with exponential smoothing. It assumes a mean of 0 on the differences. So in business day that we look at, where we're talking about sales and revenue, they should be going up or we'll get the pink slip, right? Yes? So, if we fit that, look what happens. Look at the SBC value, 1274 versus 1286. We do much better, don't we? Yes? Yes? And isn't this a more realistic set of predictions than this? Mr. Buffett, mate, your sales are just going to be flat. Revenue. Yeah, good luck with that. Yes? Now, so have a look at the difference. I've put both of these models here. This is both valid. They're both valid. But notice this model here, SBC 1274 versus 1286. We prefer this model. Now, remember when we did this, what else did we find? We found there was some outliers, didn't we? Yes?
Yeah.
How do you allow for outliers in exponential smoothing?
I don't know.
It can be done. It can be done. But it's kind of a bit of black magic. There's no way to identify the outliers.
Does that make sense though? Because it's a flat prediction. It's not going to.
Well, but again, the flat prediction, if I tell you last time there's a huge outlier, you don't want to go flat across from last time, do you?
Right. All right. But if you've got one in the middle, let's say.
Yeah, then you're fine. But you know that this is saying that the prediction is based on what we saw last time.
Yeah. All right.
Weights are most on the last value and then they diminish.
Yeah.
You better bet your house on the last value, right? So, it is straightforward to accommodate additive outliers and level shifts of the 911 model. It's more flexible because it allows for a non-zero mean. So there are two advantages that I see. It allows for the non-zero mean, and we know how to account for additive outliers and level shifts. Yes? And then exponential smoothing effectively assumes that the time series is locally stationary with a slowly varying mean. So the purist would say, yeah, we're going to have the mean, the difference is zero, because we're going to assume that. That's what the method effectively does. So we found these additive outliers last time in the homework. Remember this beautiful piece? Mm-hmm. Yes? Yeah. So we can include them and fit our ARIMA model, yes, which you did and I did. And let's look at what we get. Remember, we did much better, 59,159 versus 57,518 if we allowed for the additive outliers. Remember that? And if we didn't allow for the additive outliers, because we had a big outlier the period before, our prediction was 62,248. So, I love this example. Last year when I did it, there wasn't a big outlier in the first quarter, but there was here. So the exponential smoothing thing, or anything that doesn't take account of that outlier, is fundamentally flawed, isn't it? It's putting a lot of weight on a value which is not reliable. Yes? Not reliable. Are we good? We understanding what's going on? And then if we do the additive outliers, I'm a 1,1 versus a simple exponential smoothing, they get 63,235 and we get 59,159. So we beat the dot. The IMA 1,1 model with the non-zero mean allowing for the outliers, performs much better than the exponential smoothing, right? Yeah.
So what's the difference between this one and the previous slide?
The previous slide is the mean of 807.
Okay.
Yes? I allowed for a non-zero mean. On this slide, because we're doing exponential smoothing, there is no mean. Right? The mean difference is zero. So I guess the bottom line for me is real simple. I would much rather use a reasoned approach at looking at the data to decide the model. Yes? Like, how many times have we found I'm a 1,1 to be the best model? Not a lot, have we? What happens if it's AR? We're doing exponential smoothing. We're in the completely wrong ballpark, aren't we? Yes?
Dr. Schiller,
Yes.
can you add in jump any predictors, not just dummy variables, to the exponential smoothing?
No, not that I'm aware of. You can do all kinds of fancy exponential smoothing. You can include a linear trend. You can include seasonality. Right? You can't identify and adjust for outliers. So I'm not a fan. I just don't use it. I love to go against the exponential smoothing, folks. You let me pick, use the data to pick the better model, we'll generally beat the dot out. That seem reasonable? And remember here, if you look at the predictions, look how the prediction goes down. Because this point was identified as an outlier. You don't want to put a huge weight on that previous point, do you? So, you can go somewhere else and learn about exponential smoothing, but I suggest to you, with all due respect, you're much better to fit ARIMA models. Because one of the special classes of them is exponential smoothing. If exponential smoothing is right, that is what will pop out of your porridge. Yes? It's the same model. But we have many more tools. Yes, question?
Is there any situation where you would recommend to feed exponential smoothing instead of IMA?
If I had lost my mind, I might think that. Is that a good answer?
Yes, good.
So, Alejandro, here's the deal, mate. You have to guarantee me there are no outliers and level shifts. Yes? I don't see every data set I look at has outliers and level shifts in it, potentially, doesn't it? So, it's kind of a straw man. We beat the dot out of exponential smoothing, but my point is simple. If you believe in exponential smoothing, just use ARIMA models, and if it happens to be the right model, it's the one that will pop out of your porridge, right? Yes? Now, if you go and talk to these folks in companies, they'll say this ARIMA stuff is way too complicated. Nobody can understand what it's doing. And there's something to that, right? This has got a very simple formula, yes? But anyway, I've made a whole career with ARIMAs. Aaron?
How do you explain that to somebody that posed that question to you? I don't understand it. Is there an easy way?
Well, again, let's look at this. What does an I-1 do? We have this on the exam, doesn't it? So MA1 is YT minus mu equals AT minus theta 1, AT minus 1, yes? So it's all about the error in the previous prediction. So you have to get out pencil and paper, and it's a bit more sophisticated, but you can take it through the calculations like we did on the exams. Yeah. All right.
Dr. Shearer.
Yes, a question online. Go ahead.
So what is the difference in accuracy if you were to fit an exponential smoothing versus an ARIMA for something that didn't follow the correct order to use exponential smoothing?
Right, so you can get really horrible fits with exponential smoothing. I tried to be fair here. I picked something that was MA. So at least we were in the same ballpark. If I took, what did we look at? It was AR. If we took sales oil price, gasoline price, Netflix, exponential smoothing is horrible because it's trying to fit MA in an AR situation. Yes?
So then I guess that's why when you hear you can't model that, that's what those people are referring to.
Well, again, it's hard for me to argue the other side. What they're really saying is, I don't understand ARIMA modelling, and I know how to jerry-rig this exponential smoothing to get it to work fine.
Okay.
Whereas here, we're going to actually say even better, how do you do a transfer function model with exponential smoothing? Right? We want to get predictors in the model which will predict ahead of time when something's going to change. And you can't do that with exponentials. So the big learning for me is, and it usually pops out of your porridge in the exam, is exponential smoothing is a very restrictive choice of ARIMA model. No matter what you do, it's one choice, isn't it? Yes? And I'd rather, imagine you go to the best restaurant in the world and they say, mate, you've got to have this dish. Sam's laughing for the folks who know. It wouldn't suit me. I'm always different. Yeah.
So my question to have enough ammo, if people want to defend this thing.
Yeah.
I seen jump a seasonal, damp trend, linear, exponential.
Yeah, you can do all that, yeah.
So if I want to fight with somebody and say, okay, my model versus your model,
Yeah.
and I compare SBC, that's still a reliable metric,
Yeah.
even if the, I guess, degrees
Well,
of
what I
freedom are
would do,
different.
SBC is like this black magic that most people understand. I would compare out of sample predictions.
Yep.
Okay?
But SBC is still valid
Yes,
for
it
these
is,
ones.
yes. And so their fanciest smoothing thing is equivalent to some ARIMA model. But again, once I saw this demonstration, I went, I'm good. I know how to do ARIMA modeling. They don't have an advantage over me. They're picking from the same menu. They get to choose one thing. I get the whole menu. Right? If I know what I'm doing, I'm going to do better, aren't I? Yes? Sam?
I'm good.
Okay. Let's see if we can get out of here.
Hit Control A.
Control A. No, you're going to have to jump up. So the next thing we're going to start doing is, how do we put in predictors? We're going to do this in 2 weeks. We'll start simple with just time. And then next week we're going to do not Netflix, we're going to do Chipotle. We're going to do predict sales based on the number of stores at the start of the quarter plus the number of new stores. Because the sales from a new store are not the same as sales from existing stores. We're also going to look at plays on Broadway. Can we predict 7 weeks in a row what the revenue is for each week? It's a really fascinating problem. And challenging. We're going to look up 150 lags in some of these plots. Because it's weekly data. But, thank you. What we're going to do is start crawling along the ground. So again, that we have some principles that we can apply when we get lots and lots of complicated exits. Does that sound like a good plan?
Yep.
I think it does. So, here we're going to think about deterministic predictors. Time. Number of restaurants. How many restaurants does Chipotle have? You can look that up. How many will it have next quarter? We know that because they're being built, right? So I'm calling those deterministic. They're not another time series. Right? How many performances are we going to have on Broadway? What week of the year is it? If you go in February, that's great. If you go around the first of the year or around Thanksgiving, as we'll see, man, is it expensive to go. Hard to get a seat. But they're deterministic. Then the holy grail, which starts the week after that, is transfer function models when the x is a time series. And as we heard tonight, you've got to remove the time series part out of x before you look at it with y. It's a beautiful thing. So, I wrote this theory book once, A Modern Approach to Regression. It came out of lectures to master's students with a math background. And basically, there's straight line regression with AR1 errors. The difference here is this variance term. So the mean of the least squares estimate is the true value. So that says if you ignore the correlation structure, the slope you get is valid. That's not going to be that different. If the slope is 7.2, allowing for the correlation structure, you'll still get around 7.2. What is different is the variance term. When there's no autocorrelation in the data, you just get this term here. When there is, you get this horrible mess. You get this horrible extra mess. So all of your tests, all of your confidence intervals are wrong. All your inferences are wrong if you ignore the autocorrelation in the errors. Okay? So, let's go back to the 1930s. You've got to do a lot of this by pencil and paper. What are you going to do? Two blokes, Americans, Cochran and Irving. Figure this out. What do you think they did? Oh, the first thing I'm going to do is I'm going to show you what happens. So we're going to fit a straight line with slope 0.2 and AR1 errors of 0.7. So have a look at the residuals. The residuals, because we fit the right model, looks like, I think, an AR1 process, doesn't it? Because the PACF cuts off after lag 1, yes? Yes? Now let's look at the coefficient. We know the coefficient is 0.2. 0.2. Look at the confidence interval. The confidence interval goes from 0.017 and change to 0.195 and change. The confidence interval doesn't contain the true value 0.2. Right? So if you were doing this, ignoring the AR structure in the errors, you're wrong. You're not even close, right? The true value is 0.2, and you don't get anything like 0.2 when you do the confidence. Are we good? You understand that this is a problem? Yes? Now, when we did this in 608, we just went to a thing called mixed model and said, let's have the errors be AR1. But we'll see, man, AR1 errors doesn't work all the time. So, what you can do though, is you fit a time series model to the residuals and then estimate an AR1, and notice that the AR1 coefficient is very close to 0.7, 0.72 and change. And have a look at the residuals. What do the residuals look like? They look like white noise. So if you're on statistical survivor, you can use least squares to fit the line, take the residuals, and then fit a time series model to that.
So is that a residual plot of the residuals?
No. So what are the residuals from? That's a great question. Where did I get the residuals? I got the residuals from this line.
Right.
Okay?
And then you fit it.
Then I did it. Then I said save the residuals in jump. Save columns residuals, and then I did time series on the residuals of what?
Right. And then below, then after that, you did a residual plot of that time.
Yeah, I did a residual plot of the
Of the
residuals
residuals.
because I wanted to make sure that my AR1 model for the residuals was correct. So I've got residuals of residuals. Some of you dudes do third differences. You've got the difference of the difference of the difference. Is that complicated?
How did you know that the slope was going to be 0.2 in the first place?
Because that's the way I generated the code. Where's 0.2? 0.02 there, right?
0.02.
It's 0.02. Yes, you found a typo, Sam. Well done, mate. So let's do a little calculation. How many weeks are we? 100 slides a week times 8 weeks, and we found another typo. Well done, mate. I look forward to grading your next test. We're good. Got a good sense of humour. 1940s, these two blokes, Cochrane and Urquhart, for the ones that have math nerds, what they did was decide that if you take y minus rho yt minus 1, rho minus y rho t minus 1, you do a new regression. That in fact, these things, the errors are not AR1 anymore, because you've subtracted the rho times yt minus 1 out. So you do a new regression called y star and x star. Yep. And then that's what you get. And then you have the trouble is what happens to the first point? There's no y0. So from the 1940s, they just said, sorry, we can't fix the first point. And then in the 1950s, Prey and Winston came along with a transformation that works for the first one. So the long-winded explanation here is these two really smart guys figured out a mathematical way to change a model with AR1 errors into a least squares model with IID errors by doing this transformation. Brilliant piece of work that people still genuflect over 70 years hence. Now, what happens if it's MA or AR2?
Dr. Shida, I'm sorry, can you go back to slide 5 again?
Slide 5.
No typo.
Yeah, that typo thing.
Yeah, so this should be 0.02.
Yeah, I agree. So in that case, why would you say this is falling out of the confidence?
0.017 and 0.019.
Right.
It's not 0.02.
0.02 is still outside.
0.02 is still outside.
Okay. Okay, sorry. I got it.
So, what do they say in this country? No good deed goes unpunished. I try and come up with an example which demonstrates my point, and then I make a mistake by not putting 0.02. My bad.
That's what everybody ran was on about.
That's good. And then I'll read the evaluations, and then I'll say there's all these errors in his name.
Especially Sam. Sam, in your case, don't leave him. Don't leave him for those 2 grades.
Okay.
So, what do you do today? What do you do today? You can just use stats to fit a regression model with time series errors. And you can have any time series model you want. Right? Next week we're going to go wild with lag 7. Lag 7.
Weekly?
Sorry?
Weekly?
It's weekly, yeah. Lag 7's weird. So, and this is effectively what we've been doing. Remember when we put in dummy variables for additive outliers and level shifts? What we were doing was really doing cross-correlation is time, input is time. We were fitting a regression model with time series errors. But I didn't want to tell you that because I didn't want to get into all of those details. But that's what we've done the whole semester. That's what you're going to do this week for the homework, right? So, when you do it, how do the, well, there's the data, etc. Let's look at the output. The time coefficient is 0.01882. Right, 0.01882. Look at the standard deviation, or the standard error. 0001 versus 0004. So if you ignore positive correlation in the residuals, if you ignore it, you're going to get a standard error of your coefficients that's too small. Your confidence intervals are too narrow. Now let's try and figure out why. Imagine you have a situation, I'm going to pick on JT because he's a good guy. JT has this process where today's value is correlated with 0.99 yesterday's value. How much new information does he get every day? Very little, right?
Right.
Sandman is good buddy. He has this process where it's all over the place. But the good news is today's result is not correlated at all with yesterday's result. So every day is new information, isn't it? So if we're doing regression on Sandman's data, right, we're getting more information, aren't we? Yes? If we're doing regression on JT's data, assuming that it's not correlated, we're fooling ourselves, aren't we? So that's the point. If you have positive correlation, the new information is not as good as you think it is. So you have to have a bigger standard error, right? Yes? Bigger standard error. Are we good?
Yep.
Now, when you get away from AR1, it's really hard to intuitively know what happens to those standard errors. Sometimes they go up, sometimes they go down. Now, this is the thing which is sobering. Look at the white noise plot. And we generated data where we had a regression line with AR1 errors. And we fitted data with a regression line with AR1 errors. And look what happened. And I didn't choose. That just popped out of my priorities the first time. So it says you've got to be careful not to overinterpret those white noise plots. Right? Because if you think about it, we're doing 20 tests. One of them should be significant at 0.05. 20 times 0.05 is 1. One of them should pop over the line even when the model is correct. It's pretty sobering, isn't it? I think it is, but I'll be. Then we look at the residuals, they all look good. Now, this is the bit that I love. Here's the forecast for Y, adjusting for the correlation. See how the points go up and down, above them and below the line? And here's the forecast ignoring the autocorrelation. Because if there's no autocorrelation, if there is autocorrelation, and I tell you the last point was above the line, the next point should be mostly above the line, shouldn't it? Yep. If I told you the last point was below the line, the next point should be mostly below the line. So once I see this picture, I go, please don't make me do this. This is the one I want. Are we happy?
Yep.
Because we get the trend part, yes. We get the trend, and if it's above the line the last period, it will generally be above the line the next period. We're going to do much, much better, aren't we?
Yep.
Everybody good? Yep, I think so. All right. Now, we're going to use prop auto read. We're going to use it once, and I'm going to rant and rave and say, please don't do this again. Control yourself. So, same start. Here we just say instead of ARIMA, we do auto read. Now, Here was our AR1 coefficient, 0.72384. We know the true fee is 0.7. When you do auto-reg, look at the AR1 coefficient.
Minus.
It's minus. The first time I saw this, I thought I was losing my mind. Have you seen any negative autocorrelation in any plots we've done? Have you? No. So what you have to do is make this a plus. For whatever reason, auto-reg always puts a minus in front of the coefficient. Right? And I can't call the helpline anymore about it. I don't know why, nobody can tell me why, but it's got a minus. Does it bother you?
Yes.
It bothers me like you wouldn't believe. Why do they do that? Nobody can tell. But notice everything else is the same, except the minus. So for some unknown reason, we just put a minus in front of things, just to confuse people.
But all our other routines,
They want to
it's
sell an
positive.
upgrade.
It's positive. Just in that one, they put minus.
They're not-
Whenever you see minus, Mark, you go, no, but that's not minus. They report it as minus. You've got to minus the minus and make it a plus.
So then
Shoot me now, please.
why aren't they fixing it then? That's really odd.
They want to sell the upgrade.
Please call the helpline tomorrow, but don't mention my name. And don't mention Texas A&M because they sponsor us, mate. Make up another university, okay?
UT.
They get me soon. All right, so that was a toy example where we knew the truth. We're going to come back to Berkshire Hathaway. Have a look how linear this plot looks. Straight line is a reasonable thing, isn't it? I think so. It makes me smile. So we're going to try and fit a straight line to Berkshire Hathaway. And then we're going to try and figure out how that's different than doing differences. Right? One of those age-old problems. So you're lucky, I'm telling you all these things I've puzzled with for years by myself. By myself, when I was the only graduate student at Trove University in the 1980s. So we want to know, here's our IMA 1-1 model, right? Versus what do we get when we do the straight line. Now, I'm going to ignore the outliers for the moment, but I'm going to bring it back in. I'm going to show you this year for the first time, because I knew you'd ask. How do you fit a straight line model and allow for outliers? That's fun, isn't it? Yes? And which does better? The IMA 1-1 model, based on the differences, and allowing for outliers, or a straight line model, with, you haven't figured out what the error structure is for the residuals yet, allowing for outliers. It's just a beautiful story. It played out on Sunday. So, here are the rules. Develop a valid regression model for Y as a function of the vehicles. Ignore autocorrelation. So for my little Vegemites who were doing red light camera tickets, fog, snow on the ground, visibility. Yes? You fit those things. Model. Second step, examine the ACF and the PACF of the residuals from model 1. So if the first model is wrong, shoot yourself then and just forget about it, okay? Because you're going to get into a death spiral. You understand, right? You've got to have the right model because then the residuals resemble random errors, right? Yes? If possible, propose a model. If not, use a random model group. Then use SAS, refit the model from 1 with the errors found in 2, examine the fit from the model, and see whether it's valid. Sometimes you have to iterate through a few steps. So let's try it. So, here's the straight line, and here are the residuals. Do the residuals look, how do they look? What do we see? Do they look stationary? Sorry?
Sorry.
You see non-constant variance? You guys are so tough. Like, mate, Sam, get a job in the real world, mate. I don't see non-constant variance. I see some outliers, right? Yeah, Bernard.
What's the Y variable here?
The Y variable is quarterly revenue in millions of dollars. Okay? It's what we've fit models with before. Quarterly revenue.
Sorry, what's the predictor?
The predictor is time.
It's time, okay.
Quarters since 2000. So this says every quarter the income goes up on average by 754 and change $million. It's pretty good, isn't it? He's one of my heroes, that bloke. JT.
So you're saying then since the residuals are actually staying between plus or minus 10,000, that says the variance.
Well, again, where are you getting the non-constant variance from? This point, this point, this point.
It takes a dip. It takes a dip for that middle part.
It could be a level shift, yeah. But we know how to do level shifts and outliers. Just go with the flow, come on. Trust me. It's the second semester we've done this. Are we good? Yeah. Now, what error, what process are you going to model the residuals with? Which ARIMA? Pick one.
AR1?
AR1. Why do we pick AR1? Because the BACF cuts off after lag 1.
Yep.
And this keeps going a bit. Yes?
Yes.
And it's not perfect, but who is, right?
Yeah.
I'm not used to Dick Eisberg, but she's no longer here, so I can't use that as an example. You're going to use AR1? Yes?
Yes.
So, we're going to use AR1, we'll do model group, and guess what? AR1 with no intercept pops out of our porridge is best. Why do we always use the no intercept? Because residuals have mean zero by definition. Right? Residuals, half of them are above the line, half of them are below. They have mean zero by definition. So I'm going to do that. Are we good?
Yes.
So we feel good, we give ourselves a pat on the back, well done. We picked AR1 and so did the ARIMA model group. Yes?
Yep.
So what are we going to do next? We're going to go and check whether AR1 with no intercept is a valid model for the residuals. Right?
Right.
Just because it came out of the ARIMA model group doesn't mean it's valid. And we get a coefficient of 0.52. 0.52. And is the model valid?
Yeah.
Yes.
Yeah.
So it's really interesting. The other model is differences and moving averages. But if you put a line, we're going to do a line plus AR1. That's really interesting, isn't it? Can't wait to see who wins. Then use SAS, refit the straight line model with AR1 errors. So, here's the AR1 errors. P equals 1. Yes? We have to tell it what the predictors are. That's the input. That's the number of quarters since the beginning of 2000. And then we have to put this cross core business.
Yep.
All good? And here we go. How does our white noise plot look?
Beautiful.
Fabulous, right?
Beautiful.
Not hideous. We want to go to the Greek island fabulous.
Fabulous.
Yes? Not hideous. You don't know that story? That's what I say to undergraduates. Keep away from hideous, go towards fabulous, right? Now, here's our AR1 coefficient, 0.524. Here's our estimate of the slope, 764. Now, let's look at a comparison. The slope was 764 and change, and here it was 754 and change. Not that different, right? Look at the standard error of the slope. 18 and change versus 33 and change. So that makes sense. It's AR with a positive coefficient. So we're going to have a bigger standard error because we're not getting new information every quarter. It's related to the previous ones. We good? This is a beautiful thing. It's going well. Now, let's look at the difference between straight line and difference. Okay, aren't you curious about how the MA model with the differences matches the straight line model? So, suppose the true model is this. That means that y is a linear function of time. Revenue is a linear function of time. Let's just suppose that, right? Then if we take the difference, or Sam, I'm having a bad day, mate, yt minus 1, another typo, my apologies. Right? Yt minus 1, yt, the beta naughts are going to cancel out. We're going to get a beta 1t and a beta 1t minus 1, an e of t and an e of t minus 1. Yes? So what happens here is that the differences are all equal to the slope. Right? The differences are all equal to the slope. Makes sense, doesn't it? The slope is rise over run. It says it goes up 750 units each quarter. Right? And if we believe in the slope, quarter 1 to quarter 2 is 754. Quarter 2 to quarter 3 is 754. Right? So the straight line model has come up with one estimate of that difference, right? The differences are saying, no, this difference is every quarter. We got it? Now, have a look. Have a look at the standard error of the straight line model. It's 33, and the straight line and the standard error of the difference model is 141. Why is the standard error of these differences? Right? The difference model says I'm going to, what's the difference between this quarter and that quarter? I'm going to calculate all them and average it, right? In some sense. It gives you about the same answer. Why is the standard error much higher for the differences? 141 versus 33.
Is it because the MA just predicts the straight line?
Yeah, the one that predicts a straight line says there's just one quantity, and it's easy to estimate a straight line. It's going to give you a smaller standard error. The difference says, I'm going to monkey with each individual difference, right? And sometimes these things go up a lot, and then they go down a lot. On average, they're about the same. But we're getting, again, the straight line is saying I'm going from point A to B on a straight line. The difference says I'm going to point A to B by all these up and downs. So it has to be not as accurate, right? So in theory, if you do believe there is a linear trend, then this linear trend model should give you more accurate estimates than the difference model. But if it's not linear, good luck to you. So we're going to do both, right? This is the P equals 1 with the input. That's the regression model. This is the Q equals 1 with the differences. Remember, if you put a thing in brackets, it means first differences. Yes? And then, have a look. Do they look that different? No, visually they don't look that different. It seems reasonable here because the straight line seems like a reasonable thing. Now let's actually have a look at what happens. The revenue for quarter 2 was 57 and change. Remember when we did IMA without taking account of the outliers, we got 62 and change. Here we get 61 and change. They're both kind of bad, aren't they? Yeah, they're both kind of bad. Straw man versus straw man. So what we should do is, and then if we look at the predictions, this is the forecast from the IMA 1.1 model, this is the forecast from the regression model. Are they that different? No. If we look at the residuals, do they differ much? No. They're about the same here, yes? They're about the same. This is one of those cases where a straight line model seems to do okay, doesn't it? Now, but we know that we should have taken account of these outliers. So, guess what we do to find outliers? We prove the fit and we bring back our command outlier max number alpha. Okay, it only finds 3. What happened to the fourth one? You go and you refit, and guess what happens? The fourth one pops out of your porridge. Yes? So we need 2 steps with the straight line model to find the outliers. Yes? Now we're good to go. Our input is the x quarter since the beginning of 2000 and our additive outliers. Are we good? P equals 1 because we believe the errors are AR. Yes? And here is our output, straight line. Notice we feel good about the fact that all of these outliers have really small p-values, right? And when we compare SPCs with previous SPCs, we're still doing the right thing. And have a look at the white noise plot. It's a ripper chipper, isn't it? A ripper chipper. So we have a valid model with the 4 outliers, yes?
Yes.
Now, if you go back to your homework, you do exactly the same. Then we come and we actually say, what is the prediction? 57,015 versus 57,500. We're off by 500 in 57,000. Let's have a party. Here we go. Boss, have a look at that, mate. Pretty good, isn't it? Yes? Then how do we do with the I'm a 1-1? 59 versus 57. Straight line did slightly better here, didn't it? Straight line did slightly better. Now, I would actually use both of these in practice. They're both valid models, they're both competitive, right? But isn't it interesting? Imagine you had a predictor like the number of restaurants. That should be more information, shouldn't it? Right? If that affects the outcome, shouldn't we put that in the model? Perfect.
Yeah, Doctor, just clarification. So in this case, we happen to find the AR structure in the errors, but it could be anything, right? It could be AR, MA, R.
So next week we're going to monkey with things where P equals 7 and Q equals 1.
Okay.
Or Q equals 7 and P equals 1. It's often not AR.
Got it.
Okay? I just like the Hathaway thing because it's topical and it just fits lots of situations, right? Then if we look at the residuals from the 2 models, these 2 things look identical, don't they? Yeah. We get slightly different from point to point, but averaged over all the data, the residuals are essentially the same. So they're both competitive models, aren't they? And if both models give you about the same answer, you feel much better about than if they give slightly different answers. So what we've done, let's summarise, is we've just learned how to crawl, right? When there's one predictor. Next week we're going to put in number of performances, week of the year, and year. For the line here. And I'm going to give you something else that you get to monkey. I'll give you another play called Wicket. And I know these people at Disney who actually, because this is public data, they fit models on their own data and their competitors. It's a very competitive market. So there we have the number of performances. It can be 6, 7, and 8. We have the week of the year and we have the year. And we're going to compare a regression model, which is what they use. They say, this is the week of Thanksgiving. I know what happens in Thanksgiving. Right? This is the last week in February. It's a down week. I know what's going to happen. And then we're going to give our full tilt ARIMA modeling at it to see if we can fit a seasonal ARIMA ignoring the predictors. And for some plays, one beats the other, and for others it's reversed. But it's a good thing to have. If they both pretty much agree, you feel better about your answer, don't you? Yes? Okay. Any questions about modeling series with effectively deterministic predictors? We know how many restaurants we have, we know what day of the week it is, what quarter it is. So,
General question, if you have a situation like this where you have two models that are equally good based on SPC, and would you just pick the prediction off of one, or would you average?
I would do averages. So, you know, what with Dr. Jones, let's channel Dr. Jones. Let me talk quietly. Walk towards the camera. And he'd say, let's average the predictions. And how would you decide the weights of the average? What would Dr. Jones do? He and I are going to this conference in a few weeks. It's going to be the biggest time you've ever seen. What would he do? He would base the weights on variability, right? Which is the model with less variability would get more weight. These two are about the same, so you'd probably average them, wouldn't you? Yes? Didn't he tell you about how to do the weights?
No.
I'm sure he did, you must have been listening. You're probably too busy asking me questions.
That's the lecture he missed.
Yeah.
Because we asked too many.
Yeah, he never got to it.
Yeah, he's told me 20 times. Next year, he's got to get one more lecture.
Like Such said, that was on slide 5. We only got to slide 1.
Yeah. Okay.
What about the outliers on the straight line model?
Yeah, the outliers on the straight line model, we found them. Right? We identified the same ones. Right?
3 and 1.
If you look,
He would say, I could,
have a look how this pops up here.
and then look at top of
And
that.
it pops down there. It identifies the outliers, right? It's effectively doing the same thing. I think it's a wonderful methodology, don't you? Just another tool in your toolbox, yes? Okay, thank you for a great week. I look forward to receiving the proposals for your project. And I look forward to talking to you in the office hours.